In this video, we are using a bronchial tree input mask to create a vessel centerline calculated by the DtfSkeletonization module and visualize the vascular structures in 3D using the SoVascularSystem module. The second part uses the distance between centerline and surface of the vessel structures to color vessels depending on their radius. Add a local image module to your workspace and connect it to a DtfSkeletonization module. Load the ML image file provided in the comment of this video. Press Update button of the DtfSkeletonization. The module calculates the skeleton of the vessel tree and the erosion distances to create a new output mask. You can use a Synchro View 2D to see the difference before and after the skeletonization. The graph output of the DtfSkeletonization module shows nothing. Open the panel. Set Update Mode to Auto Update and select Update Skeleton Graph. Now the output provides a 3D graph. Additionally, enable the Compile Graph Voxels to provide all object voxels at this output. Connect a Graph to Volume module to our DtfSkeletonization module. The 3D graph is converted to a volume again. Add a View 2D and a View 3D module to see the results. For coloring the vessels depending on their distances to the centerline, we need a SoLet Editor module. Change your network to use a SoExaminer Viewer module, a SoLet Editor module and a SoBackground module instead of a View 3D module. Use the SoLet Editor for the View 2D. Open the output of the Graph to Volume module and inspect the images in Output Inspector. You will see that the HU value of the black background is defined as -1, the vessel tree is defined as 0. Open the panel of the SoLet Editor and select Tab Range. Define new range min as -1 and new range max as 0. Change to Editor tab and define a linear LUT from black to white. The viewers now show your vessel graph. Each edge of the calculated skeleton gets a unique ID defined by the DtfSkeletonization module. We now want to use this ID to define a different color for each edge of the skeleton. Add a Run Python script module to your network, open the panel of the module and enter the following Python code. First, we always want a fresh skeleton. We touch the update trigger of the module DtfSkeletonization. Then we get the graph from the DtfSkeletonization output. If a valid graph is available, we walk through all edges of the graph and print the ID of each edge. In the end, we update the Graph to Volume module to get the calculated values of the Python script in the viewers. Click Execute. The debug output of the MeVisLab IDE shows a numbered list of edge IDs from 1 to 153. We now want the edge ID to be used for coloring each of the skeletons differently. Open the panel of the SoLet Editor and select Tab Range. Define new range min as 0 and new range max as 153. Define many different colors for your LUT. The SoGVR Volume Renderer module also needs a different setting. Open its panel in the Main tab, select Illuminated as the render mode. Adjust the quality setting to 0.10. On tab Advanced, set Filter Volume Data to Nearest. Change to the Illumination tab and define the parameters as seen in the video. Change the Python script to create a property label and set its value to the ID of the corresponding edge. Your viewers now show a different color for each skeleton, based on our LUT. The SoVascularSystem module is optimized for rendering vascular structures. In comparison to the SoGVR Volume Renderer module, it allows to render the surface, the skeleton or points of the structure in an open inventor scene graph. Interactions with edges of the graph are also already implemented. Add a SoVascularSystem module to your workspace. Connect it to your DtfSkeletonization module and to the SoLet Editor as seen in the video. Add another SoExaminer viewer for comparing the two visualization. The same SoBackground can be added to your new scene. Uncheck Use Skeleton Colors and use Integer LUT on Appearance tab of the SoVascularSystem module panel. Draw parameter connections from one SoExaminer viewer to the other. Use the fields belonging to the camera to synchronize your viewer interaction. Connect the backwards direction of the two SoExaminer viewer by using multiple sync float modules and two sync vector modules for position and orientation fields. Camera interactions are now synchronized between both SoExaminer viewer modules. Now you can notice the difference between the two modules. We use SoVascularSystem for a smoother visualization of the vascular structures by using the graph as reference. The SoGVR volume renderer renders the volume from the graph to volume module, including the visible stairs from pixel representations in the volume. The SoVascularSystem module has additional visualization examples unlike SoGVR volume renderer. Open the panel of the SoVascularSystem module and select Skeleton for display mode in the main tab to see the difference. The next step is to change the visualization based on the radius information of the vessels. We will modify the existing code to use the minimum distance between centerline and surface of the vessels for defining the color. The values for the provided vascular tree vary between 0 and 10 mm. Therefore define the range of the SoLut editor to new range min as -1 and new range max as 10. On Editor tab, define the following LUT. In the Run Python script module, change the existing code to use the min distance property of the skeleton for the label. Also touch the Apply field of the SoVascularSystem module. The result is a color-coded 3D visualization depending on the radius of the vessels. Small vessels are red, large vessels are green. The SoVascularSystem module provides information about mouse clicks into a vascular tree. Open the Interaction tab of the SoVascularSystem module. In SoExaminer Viewer module, change to pick mode and click into your vessel structure. The panel of the SoVascularSystem module shows all information about the hit of your click in the vessel tree. For further information, please have a look at www.MeVisLab.de.